So we release the answer key and the grades just so that nobody has an inside track into what's on the exam. So again, we're going to look at groundwater today and surface water. And I've divided this two-day lecture into 4 parts. The first part is looking at surface water and then surface water pollutants. There's a really great table in your book that shows the type of water pollutants and from where they come and then what they do to you. So I want to say it's like 12.1 or something. I can look it up. Varies by which edition you have. But it's a really good reference for you to use when we talk about water pollution. It's great because you can see everything, where it comes from and what it does for you. So we've, at least in a cursory fashion, talked about the water cycle, about the fact that we are the blue planet, right? We have 1.36 billion cubic kilometers of water cycling around on the surface of Earth. And in Geoscience 2, if you took it or will take it, we'll treat this in a very different way. We'll look at it from how death and destruction happens from rivers and flooding and hurricanes, tornadoes, and that sort of thing. But from our point of view, we're interested in where can we get water? So where is the water that we can use? So this is the hydrologic cycle or water cycle. There's no start because it's a cycle, but it's convenient to start in the oceans. You can imagine that most of the water, I'll show you some numbers shortly, most of the water is in the ocean, and evaporation will bring that water into the atmosphere where it will rain or snow down onto the surface of Earth and then be in rivers, lakes, and streams. Most of it eventually infiltrates, becomes groundwater, and the groundwater comes beneath the surface, discharges back out into the ocean, and the cycle starts over again. So this is the whole global hydrologic cycle, and the next slide shows percentages, more or less, I mean they vary depending on which study you look at, of how much water is in each one of these reservoirs. And we subdivide them so that we can study them further. Again, I'm showing you this from the point of view of where can we get water. So there are numbers here that are somewhat large. I'll get a couple out. That are somewhat large. Certainly you don't need to try to memorize these numbers, but for the last exam, you should maybe have a feel for the fact that most of the water on Earth is in the oceans. Certainly you don't need to memorize, again, the numbers. So 96 to 98% of water on the surface of Earth is in the ocean. And I say this because I'm trying to help present in a non-biased way this hierarchy of what is a big environmental problem and what is not. You hear about regional water crises, and they can get quite challenging. However, we are the blue planet. We're not running out of water. Not only are we not running out of water, we are also being added to, I was just talking about this last night in natural disasters, because comets hit us every so often, small comets, they add little bits of water to our otherwise closed system on Earth. So we're not running out of water. There's so much water here, and we in fact have more problems associated with too much water, flooding and storms, than we have with too little water. So when we start to have crises with regards to water, it's simply a question of too many people using too much relative to what's there. It is being impacted by climate change. There are places where water is becoming more scarce, and this is a crisis in California and other places, but water, it's just that it's expensive to get water to where everyone is. So we have 97.5% of water in the oceans, and the next reservoir is glaciers. So about 2.15% of the water in glaciers. Now it's interesting to do a running total of this because when you add 97.5 and 2.15, what do you get? About 99 1/3, right? So most of the water on Earth is either salty or frozen. And then you add this next reservoir, GW is shorthand for groundwater, and that's about 1/3 as well. So we're pretty much at 100% of all the water on Earth is either salty, frozen, or underground. So the things that we think of as terrestrial beings and as people who need a constant, steady supply of water are actually minuscule reservoirs in the grand scheme of things. FW stands for fresh water. So 0.009% of water is in freshwater lakes. Again, you don't need to memorize these numbers, but just understand that the things that we go to draw water are minuscule reservoirs. Saline lakes, 0.008%. Soil moisture, that's the stuff up in the unsaturated zone that we'll talk about shortly, where there's water and air. Maybe you remember from our discussion of soil. There's water and air, and you can't make use of that. You can't draw that out in any way that's meaningful. So we have soil moisture, 0.005%. And interesting, again, last night talking in natural disasters, the two reservoirs that have the greatest potential to kill people and inflict damage, 3/4 of all deaths and damages as a result of natural disasters come from atmospheric phenomena, from thunderstorms, tornadoes, hurricanes. It's only 0.001% of all the water on Earth. So, and then the same with streams. The biggest erosive force on Earth, the reservoir, the thing on Earth with the biggest capability of eroding away and destroying Earth, 0.001%. And when we're getting water for our municipal water supply and industrial water supply, we draw from stream channels, we draw from freshwater lakes wherever possible. It's easiest, it's cheapest. Where there isn't enough, we move to groundwater. So put another way, this is same stuff, but now what we're doing is taking out anything that's frozen and anything that's salty, and you see that lakes, it doesn't get to be much bigger, right? Lakes, 0.2%, swamps, 0.02%, river channels, 0.02%, and I put this out because this shows the power of that small, 2/3 of the overall hydrologic cycle, groundwater, of all of the fresh liquid water on Earth, virtually all of it is underground. Anywhere you go, you can hit groundwater. It's just a question of how much is there, can we use it, what quality is it, and how deep is it, because it's really expensive and uses a lot of fossil fuels to pump it up to the surface. So there's water everywhere. We are habituated in this country to having huge amounts of very, very cheap water. Many environmental scientists feel it is somewhat unconscionable that we indeed flush our toilet with drinking water quality water that meets the criteria for drinkable water, federal and state criteria for drinkable water everywhere. So we have lots and lots of water in this country, especially in areas where there is a water surplus, which we've kind of looked at before. Nothing to write down about this, simply a diagrammatic or a pictorial representation of what we looked at in the first slide. So the top, there's 3 pie diagrams. There's all water on Earth. Again, the numbers vary slightly depending on which study you look at. We have about 97% of all water in the oceans. Of that remaining 2.5%, 3/4 of it is glaciers, 1/4 of it is groundwater. You get down to 0.1%. There is the stuff that is readily accessible fresh water. But I would take out the soil moisture because that's not readily accessible. We can't use that. Last way of representing it, if you have all of the water on Earth put into a 26-gallon fish tank, standard size fish tank, then only 0.8 of a gallon is fresh water, and only 1/2 teaspoon of that is readily accessible. So again, this is not a global crisis. That said, there are regional problems. We know how to desalinize. I won't talk about desalinization much in this class, but we know how to desalinize. There are 5 ways that we can desalinize water, easy to do, and the technology is well established. It all comes down to money though, right? It's super expensive and it uses a lot of fossil fuels. So we can, but we don't. So this slide, again, I think I'll just put these all out. Oh no, I'll put out the United States first. Okay. So as with some of the other problems we've looked at in this class, it may be that the most obvious solution to the problem, should you elect to care about water supply and conserving water, is not really the best solution. So I remember seeing these public service announcements when I was little, shutting the water off when you brush your teeth, taking short showers, that sort of thing. Well, if you look at the breakdown of where we use water in this country, and you should have a feel for this now, as we have discussed energy resources and as we have discussed agriculture, 41% of the water that we use in this country is for agriculture. So if you're worried about water conservation, the bigger impact you can have is by buying sustainably grown food rather than shutting off the water while you brush your teeth. That doesn't matter at all. So, and then the next biggest use is power plant. cooling, almost about as much. We take in huge amounts of water, yes, for nuclear cooling, but also for the fossil fuel energy industry. They have the same premise that we discussed with alternative energy. They're using a heat source to turn water into steam, to turn a turbine to power a generator, and that generates electricity. So then you have to cool that steam back into liquid water. So we suck in large amounts of fresh water to do the cooling. The thing that should be sort of crossing your mind now is none of these are consumptive sources or consumptive sinks, right? If we were talking about fossil fuel use in this country, you could say, oh gosh, look at how much is being used. So if we had these numbers applied to agriculture and we saw how much fossil fuel, that's a big deal, right? But when you think about watering the plants, yes, a lot of it is wasted as we discussed, but it just stays in the hydrologic cycle and circles back around. So again, not a huge problem. Industry, 11%, and then 10% is public. So when you're targeting your water use, you're only targeting 10% of the problem. So this is just some interesting, I put this out of sequence, China should be next, but some interesting requirements. Again, nothing to memorize, just to give you a feel for how very much water is used in different things. 800 gallons of water is used in many different ways to make 1 pound of beef. 100,000 gallons for a car, and 1,000 gallons, this is important, we talked about recycling, right, for a pound of virgin aluminum. So another place where you could make a difference in water use is to recycle aluminum, because as we established, bless you, as we established, the use of recycled aluminum is responsible for 95% less water use. So you would use very small amounts of water if you're recycled aluminum. Throwing a can in the recycle bin is much more important than taking a short shower. So how does the United States stack up to China? Well, China, you can expect these numbers to change rapidly as they're undergoing their expedited industrial revolution. But right now, up to 90% of the water use in China is for agriculture. There's a lot of rice grown in China. Rice is a flooded crop. It can only grow in standing water. So there's a lot of water that's used in agriculture. 7% industry and 6% public. Again, as China undergoes its industrial revolution, you'd expect the numbers to shift, right? So there'd be more percent of water use in industry and public. However, you would increase the overall water use, right? Because you're using more and more water in an industrial situation, and so overall there would be more water use. So the United States and China have two very different numbers with regards to agriculture use, and a good global number, average number, for how much the world uses water in agriculture, 70%. So lots and lots of water gets used in agriculture, and as we established, when we talked about agriculture, again making these connections, because of the slotted hoses that are put 7 or 8 feet above the crops, about 60 to 80% of that is wasted by evaporation, by inappropriate watering techniques. To bury that hose would immediately ameliorate all that waste. So yeah, this is a class in science. However, this has big political and economic ramifications. I think I may have told you this again, forgive me, I never remember what I say in which class, but in California, where there are water problems, the farmers pay so much less for water per unit volume than industry and public does, that in the past several years it is actually more profitable for a farmer to not grow food and to sell his or her water rights to industry than it is to grow the food. So also something that you should think about. How does this impact the future? What is going on? How does this impact supply demand of food? And then also, is it a good thing or not? We talked about how leaving fields fallow is really important, right? And so is it unconscionable that these farmers are sitting around watching, I don't know, Geraldo Rivera and not farming while their fields are laying fallow? Or is that a good thing? Now we can redistribute water, we can let the fields regenerate, we can let pests go away. We're producing too much food anyway, so maybe that's a good thing. Again, you have to decide what you think of this. So here's a picture of, obviously, the United States. 3 colors on it. One, major metropolitan areas. So the dark blue or purplish blue, those are areas where there are lots and lots of people. The pale blue is an area of water surplus. And you do simple mass balance to figure out in an area whether you have a water deficit or a water surplus. It's very simple. You take people out of the equation. You just figure out how much water comes in by rain, and you subtract how much water leaves by evaporation. And in this whole part of the United States, again, we talked a little bit about weather patterns, right, or air masses. The whole first third of the United States coming in from the East Coast, we get more water as rain than leaves. We have a water surplus. We have a very wet area. Again, interesting, I was talking last night in natural disasters about droughts. We don't have any problems with droughts on this part of the country because we have so much water. And it's a kind of happy situation, right? Because this is where all the people live. People live in this country where the water is. That said, especially if you're from around here, I'm sure you've heard of water bans where you can't water your lawn, you can't do this, you can't do that with regards to water. You can have regional shortages where there are too many people in an area that are using up too much water relative to how much comes in. And you get into details such as interbasin transfer. So I was expert witness and a consultant for the town of Hingham, who was trying to kind of sue there. They have one of the few privatized water sources in the country, and ironically, right, not so, they have the highest water rate in the country. They pay more for water in Hingham than you do in the desert. It's because the people that own the water company are making a profit. So what they're doing is taking water out of the subsurface, providing it, selling it to people, and then they're doing interbasin transfer. So they sewer it out of the system. So you have a lot of use of water in Hingham, and then it's not going back into the system. Like if you had a septic or a wastewater treatment plant that discharges water back into that basin, you would recycle it. So they have a one-way flow, and it's interesting because they say to their residents, oh, we don't have a lot of water here, so we have to charge you a lot. And then they'll say to the neighboring towns, we have excess water, so you can buy some of our water. So they're pumping the heck out of the groundwater, selling it to Cohasset, selling it to the neighboring towns, while charging huge amounts of money for it. So this is a problem with regards to water supply. You get into economics if you have privatized sources, and you get into politics if you have too many people relative to the use. So overall, though, the picture in our country, and especially on the East Coast, is a happy one. We don't have problems with water. The yellow area is an area of water shortage. I would like to underscore the fact that this water shortage is not because of anything we did. This is not an environmental problem we caused. This is because the air mass that is hitting this region comes up from Mexico, and so the air comes off of the ocean. It has a lot of moisture, and as soon as it hits over land, I'm going down here because it's in Mexico, the moisture starts raining out, and then it moves up Mexico. It's hot and dry. Again, natural climatic things have been going on since the continent looked like this. So by the time the air mass reaches this region, there's more water in it. So it's hot and dry. And we humans like that climate, right? Everybody wants to go and retire in Arizona, retire in the Southwest. You always hear it's a dry heat over in the west side of Texas. So it's comfortable for us, but it's comfortable because there's no humidity, and so there's not a lot of water here. This is a problem for two reasons. Number one, we're starting to move into this area more and more, and we expect to live the way that everyone else in this country lives. We expect to have a swimming pool. It's amazing. People have swimming pools in Arizona. They have 11 inches of evaporation per day. It's hot and dry, and you just keep filling the swimming pools, filling the swimming pools. And then they have sprawling lawns from an aesthetic. We've talked briefly about lawns in this country. So the point is, you can't do those things without having an import of water from elsewhere. And we'll look at how we do water transfer. But more notably, there's this contentious issue in California. And I have a slide on this in a minute. But you see that most of the population, or a lot of the population from California, lives in the south, in a dry area, except for you have these brief periods of floods, but in a dry area. historically what we've done is to take water from the north where there is not a shortage. So the blue is a surplus, the rest of the country is sort of, balanced more or less. Take water from the northern part where there is water and transfer it down to the south where people need it. Why do I care about this, you may ask? I don't live in California. Well, you should care about this because 90%, bless you, of the fruits and vegetables that we grow in this country are grown in the San Joaquin Valley, this dry area. It's great from an agricultural point of view, right? Because it's hot, it's sunny, plants grow like crazy, but it's not good from a water point of view because we have a constant need for water to come from the north by these aqueducts, and we have a constant need to suck groundwater out of the subsurface like crazy. That has led to up to 25 feet of sinking or subsidence of the land in this region as a result of our centralized agricultural regime. We grow all our food there. So again, this is not to attempt to vilify the agricultural system and just saying, we try to optimize on this stuff. The climate is great for it, but we are running out of water in that area. And I think that's the next slide, actually. Oh, no, a couple slides. We'll talk about it a little more. So what are these all out. Oops, sorry. What are the causes for shortage? A lot of them are, or some of them, two of them, half of them are natural, right? So a dry climate. When people move to a dry climate, there are many good things about living in a dry climate. Having a surplus of water is not one of them. So when you start to move more people into an area that has a water deficit, you have a shortage. There are also areas, and they're getting more prevalent as a result of climate change, that have a drought. Again, natural disasters. Last night we talked about what categorizes a drought. Different countries have different definitions of drought, but it's a period of less than normal rainfall. So if you're habituated to getting a certain amount of water in an area from rain, and then that doesn't happen, then you can have problems with agricultural supply, you can have problems with water supply, you can have all sorts of problems. So a drought can be natural, can be exacerbated by climate change, but this can make for water shortage. We looked at deforestation and overgrazing as a result of our inappropriate agricultural techniques over the last couple of weeks. But what we didn't say is that this also impacts water supply. Remember we said when there's bare soil, the water hits and runs off and takes the sediment into surface water bodies or away from the land where it's needed. The other part of that is the water goes away, right? When you have rainforest, when you have even agricultural fields that are completely covered, the water comes and hits the plant and infiltrates preferentially, so you build up a water reservoir there. When you don't have any sort of vegetative cover, whether it's plants that we're eating or plants that the cows are eating, overgrazing, the water hits and runs right off. And so no water builds up. And they're like Kenya, the Mau Forest, there are places where it's a rainforest, but because of massive deforestation, they have a water shortage. It's astonishing to have a shortage of water in a rainforest. And the springs are drying up, people's water supply are drying up because of deforestation. So here's an example of human-created water shortage by agriculture. And then, I've already said this, we don't need to belabor a point, increasing demand. Move too many people into one area, use a lot of water per person, and you end up with a shortage. Not because the water went away, but because the people are using too much. I'm sorry, I'll just put these all out so I don't have to keep coming. Oh, sorry. Over. How can we supply more water? Well, in places, in the next slide I'll talk about California, in places where there is a water surplus, it's possible to do some sort of dam on a river and build up a big reservoir. Do you know where your water comes from in Boston? No? The environmental history of Boston is so fascinating. I should develop a whole course on this. So neat, so neat. I'm going to tell you about some of this. On the 20th, is that next week? I'll tell you a case study of groundwater in Boston. But historically, what has happened was in Boston in the 1800s, people started moving here, people started moving here, people started moving here. Water was a problem. We didn't know where to get our water. We didn't know where to get our water because We're ringed by ocean. Back then we weren't desalinizing things. And we were discharging our waste directly into the rivers and lakes and streams and the tidal mudflap that Boston was primarily. So all the surface water was polluted, and then we had salt water. So it became a crisis. People wanted to move to Boston. Boston wanted to urbanize and wanted to, become a big global city. We had no water. So we looked farther and farther and farther and farther west. Sorry, let's see. This way is west, yes. Farther west, and we hit upon a river called the Swift River. And Boston politicians, et cetera, thought, well, this is a great place to build a dam and build up a big reservoir so we have a huge body of water, and then we pipe that water out to Boston. Anyone know the problem with this? There were 5 towns on the Swift River. And it's really neat, again, for the sake of time, I won't get into it too much, but Boston had to buy up all of the land in all 5 towns so that they could flood the towns. And an unscrupulous developer got wind of this and started buying up the land, and so sold it back to Boston at extortionist prices. So it cost Boston a huge amount of money. But eventually they bought up all the land, they put a dam, and they flooded this whole valley. They left the houses there. So it's neat to have this video under Quabbin. Somebody got permission to go scuba dive there, and he actually sort of walked down the main streets of these towns, and the houses are all still there. And in times of really low water, you can see the tops of church steeples. And there are little islands in Quabbin Reservoir, and never happy when I do this. And the islands are former hills. So this is what it looks like. This is Quabbin Reservoir. And there were all these towns that were on. Some pictures there. Here's a map, okay? Here's a map. Oh, this is a better map so you can see. There's where Boston gets its water, the Quabbin Reservoir. Couple of things. One, it's kind of neat. They brought the water out in these big, giant, hollowed out logs. And in the 80s, we replaced the last section of this with concrete. So water was coming to us through hollowed out logs. And then also, there's a little poltergeisty, I don't know if you get that cultural reference, but they were told they had to move the graveyards. That was one thing they had to do before they filled this. And the guy who was scuba diving went and looked and found they only moved the headstones. They didn't move the graves. So think of that next time you're drinking water. That said, the water quality in this reservoir is immensely pure. It ranks consistently among the best in the country for municipal water supply, so nothing to be afraid of. But so that's where your water comes from, the Quabbin Reservoir. We take water in this state from an area of water surplus, and in this sense, it's not terribly different climatically. It's just that there are no people that live there. We build it up, and we send it out to a place where there are lots of people. And this has served us well for a couple hundred years. So not bad. Water supply. We'll see where some places can be a problem. Water transfer is dams and reservoir, and water transfer I talked about with Boston both. You build up the dam, build up a reservoir for a constant source relative to a stream, which is always moving up and down. And then the water transfer is just bringing it from a place where there is a true surplus to a place where there's a major metropolitan area, place where a lot of people need it, or a place where there's a lot of agriculture, which is next. Another way we can supply groundwater, virtually anywhere you go on Earth, unless you're on a volcano, you can tap groundwater, bring it to the surface, and you have a new source. That said, it's very expensive to drill these wells, and it uses a lot of fossil fuels. The pumps have to be going nonstop. So we prefer not to do this for one reason: it's expensive. But then you don't have this big footprint on the Earth of a big reservoir. And then I have a slide on this, so I won't say anything more about this. Using water more efficiently. We waste huge amounts of water. We waste so much water. Another example, sorry, this is my field, so I have a lot of stories about this. So I teach a class called Applied Hydrogeology. And when I teach this class, I don't teach it here, I teach it elsewhere, I have the students make a map of groundwater underneath the campus, because there are wells that have been put in for construction purposes, et cetera. And they make this map and they freak out because under this building, there's a huge mound of groundwater, huge mound. And they come to me with great trepidation because it's senior level class, they're supposed to be smart by then. And they say, oh, Professor Cole, look, this doesn't make sense. Everything else makes sense except this huge mound here. Can we just disregard this data point? And I play stupid, of course, because I like to train the seniors to think. And I say, well, was there a problem with the well? Well, no. Do you want to go out and remeasure it? Okay, they remeasure it, same point, very high. I said, well, map it, see what's going on. And so it's this big bullseye pattern of this huge, weird mound. And they're sort of shaking as they hand it to me. And then I tell them, because I'm mean, there's a big rupture in the water main that brings drinking water to the campus. And it's leaking huge amounts of water, and that's what's making this huge mound. And then they get all outraged and say, we have to fix this. You know, students that are environmental in nature, they activists. So we have to fix this, and they go to physical plan and they say, you have to fix this. This is our tuition dollars, and it's all water going down into the ground. And the physical plan is nice with them and says, well, you know, we know that it's there, and we calculated the cost of groundwater versus the cost of ripping up that whole area, and part of it is under a building. And the payback time, which is what physical plant people are always interested in, is 800 years. So they say, we'll just let it leak because it will, you know, take 800 years for us to make back all the construction costs in an urban area for this cheap water. So they get frustrated, but I mean, it's kind of a good news story, right? Water's really, really cheap. There's plenty of it, and it's not going away. Where it is a local shortage, it is fairly easy to implement ways by which we can use water more efficiently, which we'll talk about in the next slide. So our long anticipated case study. Here's California, and in a nutshell, without getting too verbose, most of the water, as you can see, is up in the north. Again, it's not a water surplus, but they get plenty of water. Plenty of water here. Salton Sea is drying up. It's going away. It was saline anyway, but it's gone. There's a really neat film, if you're interested, Pleasures of the Salton Sea. It's really sort of interesting, narrated by John Waters, a cult classic. And then we grow all of our food in the San Joaquin Valley. So historically, the way that it's worked is we have brought water from the north via dams, aqueducts, water transfer, and then also from over in Arizona, Colorado, Nevada, sometimes bring water into the southern part of California. This worked for a while, as it has worked for hundreds of years in Boston, but now recently we're seeing that the San Francisco Bay is getting more and more polluted. The reason it's getting more and more polluted is because the water that typically flushes the bay and brings that pollution into the ocean where it can be attenuated, at least a little bit, is being brought to Los Angeles. So the water's just sitting there, and you have it's ringed by urban land use, and so it's getting more polluted. The other thing is you have fish, salmon, that are a vibrant part of Northern California and then up into Oregon and Washington's economy. And the fish are hatched in a river, and they swim down the river to the ocean. They spend their lives in the ocean. We talked about salmon, right? Farm-raised versus wild-caught salmon. They're swimming around in the ocean, and then when it's time for them to spawn, they come close to the shore. They find the freshwater pulse of the river from which they came, and they swim up to it, and they spawn, magnificent really, in the same place where they were born, and then they died. These fish can no longer find the freshwater pulse because we're moving all the water down to Southern California, so the fish never get to spawn and they just die without reproducing, so the fishing industry is collapsing, the salmon industry. There are no more salmon, and it's because we're transferring water to Southern California. So Northern California is saying we need to keep more of our water, and Southern California is saying absolutely not. We actually need more of your water than you have been giving us. And it's tough because it's one state. So it's not like states are fighting against each other. It's one state. So it's really a contentious issue, and it's becoming more and more so. And it does bear sort of your scrutiny as a member of the United States, most of you, because this is where your food comes from, the San Joaquin Valley. So there are some shortages that we can point to that are local in nature and that are a result of water transfer that no longer works. What can we do? I think that's xeriscaping is the last thing. Yeah, sorry. Okay. What can we do if you're writing these down, maybe leave a little space. What can we do? Number one thing we can do is to be better with watering. Remember, global number, 70% of the water we use is in agriculture and 60 to 80% of that is wasted. We waste most of the water that we have. And so that's a real easy fix. We don't do it a lot of times because it is expensive. They're starting to implement these things in California in places where there are water shortages. So that's good news. Very easy fix for the number one huge, biggest waste of water. Recycling. This is not something that you see around here because we don't need to do it. But in places where there are water shortages, where water is starting to be a crisis, it's possible to recycle water. Does anyone know what gray water is? So it's water that's not dirty, but it's not clean either. You wouldn't want to drink it. So for example, you took a shower this morning, some of you, and when you take your shower, yes, you use some shampoo, you use some soap, whatever it is, you use shave cream, whatever, and that does get into the water, but relative to the volume of water that you've used for your shower, it's not a lot of stuff. So that water, again, you wouldn't want to drink it, but it's not toxic. So where there are places of water shortage, it's possible to, instead of just sewering that away, to put it in a tank in your basement and then pump it into your toilet or water your lawn with it, right? You don't need to flush your toilet with water that meets the United States maximum contaminant levels of every criteria pollutant there is. So can you have some soap in your toilet? Sure, and that would save a lot of water. Can you water your lawn with this? And plants actually love these nutrients that are in shampoo and soap, etc. Can you wash your car with this? Are there other things? Can you wash your pavement, whatever it is people do with water that doesn't need to be drinking water quality water? Same thing, watering your lawns. Do you need to do that? So we can use gray water as a way of using water twice in your home before you sewer it away. I already talked about repairing leaky pipes. Where it makes sense, a lot of water pipes leak, small or large amounts. We don't care about that here. And yeah, but the payback just doesn't work. We don't care about this. I'm pausing because I'm going to tell you next week about Boston's sewer problems. Fascinating sewer problems. So you can repair leaky pipes where it makes sense, both from a water supply and from wastewater point of view. We can conserve water, right? There are ways we can conserve water. Low flow shower heads. That becomes a quality of life issue, right? So I run to work in the morning, and when I go to the gym to take a shower, not here, elsewhere, it's so awful. There's these low flow shower heads. I feel like someone's spitting on you. It takes forever to take a shower. So, I don't love those. But I guess when you live in a place where there is a big water shortage, you don't need that water pressure. Toilets these days. There's a lot of engineering with toilets. I find this fascinating too. So the old toilets used 8 gallons per flush. And so they would dispose of waste by just volume of water. But as we start to realize that it's not a good idea for everyone to be using 8 gallons of water every time they flush the toilet, the engineers that work on building toilets and creating toilets have now dealt more with plumbing to forcefully bring the water down, and they can get water down to the lowest I've seen is 1.4, and it's funny in this business of trying to make really high efficiency toilets. The holy grail is a 1 gallon flush, but the problem is when you get below 1.4, then it just doesn't work no matter what the plumbing engineering is. So then you have to flush twice, and that negates the whole point of having low flow toilets. So it's fascinating. Talk about this a lot in higher level water resources classes, toilet engineering. You can conserve water. And then xeriscaping is, zero means dry. So xeriscaping is a way that you can live in a desert and be more harmonious with your environment that is not having a lawn all over your property. Xeriscaping, dry landscaping. So using the native vegetation. So if you live in the desert, maybe put cacti in your front lawn or rock, anything that doesn't use water. So xeriscaping around here would be, you maybe have seen this ground cover that is ivy or something like that. It's not a lawn, but it's native vegetation that's from around here that doesn't require any water, can just grow with small amounts of water. So xeriscaping, dry landscaping, changing your lawn and your property so that it doesn't have a huge amount of water going into it. So again, we're going to do surface water, which we just did. Surface water pollution, then we'll move to groundwater, groundwater pollution. And I'm going to do a case study for Boston. So there are two types of pollutants. We talked about this. This is the first day of classes, right? Point source and non-point source. This holds true for water. It's going to hold true for air pollution as well. Point source, in this country, have been really good at cleaning up point source pollutants. This is an example of a point source. You have a pipe. It is discharging polluted water into a river, and the fish are getting sick. We've cleaned virtually all of this up. There are illegal dumping activities, but we've cleaned this all up. The water pollution that confronts us now is something called non-point, which means you can't indicate a source. It's coming from everywhere. And I'll show you this when we look at groundwater pollution. It's coming from everywhere. We just talked about agriculture. We talked about all those agrochemicals. You can't say necessarily when water is coming into somebody's well that has a high concentration of some chemical in it, exactly the source in the Midwest, because the whole Midwest is farming and everyone's putting that in. So non-point is, you can't point to a source. This is up to 70% of the pollution in this country is non-point source for water. So it's very hard to pinpoint, therefore hard to remedy. This again is the table that you'll see in your book. I think it's a 2-page table in most editions. I will refer you to this as a companion to this slide. And there are 8 different types of water pollutants. I think I mentioned this when we were talking about agriculture. When I developed the higher level class in eating and the environment, I thought, oh, I'll take the intro level slides and just sort of modify them and figure out which of the pollutants are native to agriculture and just take out anything that's not. And it's startling to me that all of these come from agriculture, all of these. It's amazing, primarily or at least secondarily. So the types of pollutants are, again, if you're writing these down, I would leave some space. Infectious agents, anything that makes you sick, any disease that can be transmitted. So we're talking about bacteria, viruses, amoebas or protozoans, some sort of living organism, microscopic organism that can be transmitted in water and make you sick. And we have I hate this phrase, but it's zero tolerance. We don't allow any infectious agents to be transmitted to water, municipal water supply in this country at all. Zero. You cannot supply people water that has any infectious agents in it at all. It's easy to kill these. Sometimes you just sit and let them wait. Viruses, bacteria, they have, in certain conditions, they have times to extinguishing. So you have a certain period of time and they can't live anymore. Also, really, really neat, when you have a water treatment plant, 98% of all bacteria and viruses are sorbed onto sediment grains, so clay and silt particles. So if you want to get rid of 98% of all of the bacteria and viruses, all you have to do is let the water sit for a while. In a still fashion, the sediment will drop to the bottom of that tank and you've removed all of the pathogens. People add chlorine, people add ozone, we'll look at this, but really you just have to let it sit for a little while. So infectious agents, number 1 pathway, agriculture, animal waste. The next one is oxygen demanding waste. We looked at this when we talked about sediment, again in agriculture. We said sediment in and of itself robs a surface water body of oxygen, right? So, and then it also has these chemicals on it, which is inorganic and organic. So sediment pollution in surface waters, those 3. Anything that robs the water of oxygen, sediment from agriculture, and then also animal waste. The reason something would rob the water body of oxygen is because there's organics in it. Not in the way that the next organic, I'm using organic differently. Organic material, waste products of humans, waste products of animals, things that have carbon-carbon bonds or carbon-nitrogen bonds. And when you break those by decomposition, you use oxygen. So when you put human or animal waste into water bodies, oxygen goes away. So both of those come from agriculture primarily, not exclusively. Inorganic chemicals are things like metals and salts. So if you have, okay, so we talked about fossil fuels, acid mine drainage. So things like iron going into water bodies and changing the color, changing the water quality. So inorganics, metals and salts, they come from mining and mineral resources, which we discussed. Organic chemicals, this is not what I'm using the oxygen-demanding waste from. This is organic chemicals that we've synthesized in a laboratory. So organophosphates, pesticides, rodenticides, fungicides, any sort of killing agent that we use in agriculture. So organics, again, meaning synthesized organic chemicals that you learn about if you take organic chemistry that we use primarily for pesticides. They're also in the dry cleaning industry. And you can call oil and gas organic chemicals because they are these organic molecules. Nutrients, fertilizer, that's it. Sediment, again, in and of itself, it is a pollutant because it is oxygen demanding, but then also the sediment comes primarily from agricultural land, goes into water, it has all those chemicals on it and they desorb through time. I said last time like a time-release vitamin, so this will produce water pollution that wouldn't have otherwise been there. So it's really important to cover terrestrial portion of the land with vegetation. Radioactive materials, strangely, or not so strangely, because you know this now, does not come from nuclear power plants. Radioactive materials come primarily from coal-fired power plants. There are other sources, but that's the number one pathway by which water becomes radioactive. To be near a coal-fired power plant is to expose yourself to, estimates vary, but about 300 times the radioactivity that you would be exposed to if you were in a nuclear power plant. And then the last one, thermal pollution this is from nuclear power plant and also from fossil fuel power plants. Cooling water, so back to the second slide we looked at. We have steam that we generated to turn a turbine powered generator. That steam needs to be cooled back down into a liquid form so that it can come around again. And it's cooled by, remember the diagram of a nuclear power plant, sucking large amounts of water out of a surface water body, river, lake, stream, whatever, and bringing it in indirect contact through pipes with the steam, and that causes the steam to condense, and then you dump it back out into the ocean, river, lake, stream, whatever. Thermal pollution is bad because it robs the water of oxygen, and it also mobilizes metals and anything that's inert in the sediments. The warmer water is, the more metals and chemicals it can hold. So when you spew out warmer water, you mobilize anything that's sitting, in a dissolved out, precipitated out phase in the sediment, and the water suddenly becomes toxic, potentially, as a result of simply raising the temperature. Also, the warmer water is, the less oxygen it can hold, so all the fish die. And we are out of time, so we'll pick it up next time.